Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Young's double slit experiment. Let's begin. The scientist Thomas Young in the year 1801 demonstrated the phenomenon of interference of light by using the principle of superposition of waves. In this experiment, he was able to obtain the visible effect of the superposition of waves, and he could determine the wavelength of light, that is the phenomenon of interference was well established by this Young's double slit experiment, and by using that superposition of wave concept, it easily seen how exactly if the waves are superimposed with each other, then what happened. And again he so determine the wavelength of light. The wavelength of light is determined by using Young's double slit experiment. That Young's double slit experiment gives an idea the visible effect of superposition of waves. So, what be the experimental setup of Young's double slit experiment? Look here, these are the parallel beam of monochromatic light, parallel beam of monochromatic light is allowed to fall on a narrow slit S, and then a two narrow pinhole slits S1 and S2. These are placed symmetrically with respect to S. This is a single slit, one hole, that is a double slit, two hole. These slits are very close to each other, so the distance apart between them is small d, and the distance between single slit and double slit, that capital D. When one slit is open, means that single slit is open, let that slit is closed, the other is closed, then we obtain general illumination on the screen, means the light passes through that of screen and we observe general illumination, means a bright spot on that of screen. But when both the slits are kept open, we obtain alternatively bright and dark bands on the screen. On some points of the screen, we obtain that is the maximum intensity, and these bold lines are the dark, that is the minimum intensity. These maximum intensities, these are the maximum intensity, that is the maximum intensity is known as maxima. That with the minimum intensity, we have the minima, that is the screen as we placed. These are the fringes. And the distance between two consecutive dark or bright fringes is known as the fringe width. That is the distance between two consecutive dark fringes or consecutive bright fringe is known as fringe width. Here the slits S1 and S2 are very close to each other, means that distance D between them is approximately 1 millimeter apart. This double slit is placed at a few centimeter from that of single slit. Small d is very small as comparison to that of capital D. The light coming from these slits behave like a coherent source. The light coming from the slits S1 and S2 behave like a coherent source. Coherent wave or coherent source means the phase difference between the waves that coming from these sources are constant. The interference pattern is formed on the top screen, which is consist of large number of equally spaced alternate dark and bright fringes or dark or bright bands, which is called fringes. These are called the fringes. These are running parallel to that of slits. The Thomas Young, the scientist, was able to prove the phenomenon of interference can only be explained by using Young's double slit experiment. If we consider the wave nature of light, light has dual character, particle as well as wave, but Young's double slit experiment confirmed the wave nature of light, and the particle nature of light was easily verified by Einstein's photoelectric effect. So here, why the maxima or minima we obtain? Since we consider the wave nature of light, means light as a wave, from source S1 there will be a wave, and from source S2 there will be another wave, and these two sources are coherent waves. Therefore, when the crests of two interfering waves superpose, they gives rise to maxima. If that's a wave, that's the another wave, that is the crest, that is the trough, that is the crest, that be the trough. If crest of that wave is superimposed with the crest of another wave, the resultant we get the maxima or the bright fringe. Then if the crest of that wave is superimposed with the trough of another wave, then we get the minima, that is the dark fringe, as we discussed in previous videos. Now the lines of maximum amplitude Here we get the lines of maximum amplitude is known as the antinodal lines. The lines of maximum amplitude is called antinodal lines, and similarly that of minimum amplitude is called nodal lines. Antinodal lines, these are the nodal lines. Now, what be the conditions for maxima and minima? Let me discuss it mathematically. Conditions of maxima and minima. Maxima for bright fringe and minima for dark fringe. Here in case of maxima, the waves crest to crest or throw to throw, that is the constructive interference. Then in case of minima, that is crest to throw and its throw to crest, therefore we get destructive interference. The conditions for maxima and minima. That will be the slits. Two slits, here S1, S2, these are separated by a distance small d. Sorry, at that case the capital D is the distance between the double slit to that of screen. Okay, double slit to that of screen. Now there will be a screen. Which is at a distance of capital D from that of double slit. The small d, that is the very small distance, means S1 S2 are very close to each other. As comparison to that of capital D is large distance, that is just like in centimeter, this distance just like in millimeter. Here I take a point P at which you observe that is a distance of x from S1, also a distance here x plus del x, x plus del x means the path difference between these two is del x. Here the distance d by 2 d by 2 and the total distance is d. And let me take that P point is at a distance of yn from the center O. The two light waves having the same angular frequency. Let that angular frequency be omega, coming from the coherent sources S1 and S2 reach at point P on that of screen, and these waves, that wave from S1 have amplitude R1 and the wave from S2 have the amplitude R2, and they are travel towards the screen with same phase. So the displacement of these waves emerging from S1 and S2, from S1, that wave emerges from S1, its displacement y1 is equal to its amplitude R1 sine angular frequency omega t minus kx. That equation number 1. And the displacement of the wave, that from S2, y2 is equal to R2 sine omega t minus kx minus phi, where phi is the phase difference. Phase difference. Look here. Here the path difference is del x. We know a relation between phase difference and path difference. So at point P, phase difference is equal to 2 pi by lambda into path difference. It is a relation between phase difference and path difference. So phase difference here, phi is equal to 2 pi by lambda into path difference, that is del x. Here x plus del x, so path difference is del x. Now we are applying the principle of superposition of wave, then the resultant displacement, applying the principle of, that is equation number 3, superposition of waves. We have the resultant displacement at point P, that is y is equal to y1 plus y2, that is the resultant displacement at point P, which is equal to R1 sine omega t minus kx plus R2 sine omega t minus kx minus phi. Here I use sine a minus b concept. So R1 sine omega t minus kx plus R2 sine a minus b, that is sine a sin b minus cos a cos b, sin a cos b minus cos a sin b. That formula is used here. Sin a cos b minus cos a sin b. Here are two, sin a omega t minus kx, omega t minus kx, sin a cos b minus cos a sin b. From this we take sin omega t minus kx, sin omega t minus kx as common. We have r1 plus r2 cos phi sin omega t minus kx minus r2 sin phi cos omega t minus kx. Now we use r1 plus r2 cos phi as r cos phi sin omega t minus kx, again r2 sin phi as r sin phi cos omega t minus kx. I write here the substitutions as we used here. The substitutions are r1 plus r2 cos phi is equal to r cos phi and r2 sin phi is equal to r sin phi. Now taking r as common, rearranging the terms are sin omega t minus kx cos phi minus cos omega t minus kx sin phi. Here sin a cos b minus cos a sin b, this sin a minus b, r sin omega t minus kx minus, okay, here I use the angle is cos alpha, let here sin alpha, cos alpha, sin alpha, so omega t minus kx alpha. In case of the substitutions, r cos alpha, r sin alpha, okay. That for resultant displacement y. Here r be the resultant amplitude, thus the resultant wave, that is the resultant wave is a harmonic wave having frequency omega and wavelength, but the different amplitude is the r, which is a, thus the resultant wave is a harmonic wave. Y is equal to r sin omega t minus kx minus alpha. Let us calculate the amplitude of the resultant wave. How to calculate the amplitude of resultant wave? Look at the terms. Here the substitution r1 plus r2 cos phi is equal to r cos alpha I, and r2 sin phi is equal to r sin alpha, squaring and adding, squaring and adding, equation 1 and 2 we get here r square cos square alpha plus r square sin square alpha, r square cos square alpha plus r square sin square alpha is equal to r1 plus r2 cos alpha whole square plus r2 sin, here cos phi sin phi whole square, or r square taking as common, so cos square alpha plus sin square alpha is equal to, now expanding it by using a plus b whole square, r square plus r2 square cos square phi plus 2 r1 r2 cos phi plus r2 square sin square phi. Here cos square alpha plus sin square alpha is equal to 1, therefore r square is equal to, again r1 square, in that of case r2 square as common, so cos square phi plus sin square phi plus 2 r1 r2 cos phi, cos square phi plus sin square phi is equal to 1, therefore r square is equal to r1 square plus r2 square plus 2 r1 r2 cos phi. Let the resultant amplitude r is equal to under root of r1 square r2 square plus 2 r1 r2 cos phi. Here we know a relation, we know that the square of amplitude is the intensity of light wave. The intensity of light wave I is equal to k r square, where k is the proportionality constant, k proportionality constant. Let I use that concept here. The intensity I is equal to k r square, or I is equal to k, in place of r square we put all these values as r1 square r2 square plus 2 r1 r2 cos phi. We have k r1 square k r2 square plus 2 r1 r2 k cos phi. That for I, or I is equal to I r1 square, that is I1, plus k r2 square, that is I2. Similarly 2 k r1 as under root of I1, r k, that is r2, that is under root of I2 cos phi. Here we take I1 is equal to k r1 square, that is the intensity of light wave coming from slit S1. Intensity of light wave coming from slit S1. Similarly I2, that is k r2 square, intensity of light wave from slit S2, intensity of light wave from slit S2. Here we have the resultant amplitude and the intensity of the light wave. For constructive interference, what we observe, that cos phi is maximum means we get the maximum intensity. For condition for maximum intensity, that is for constructive interference, cos phi is maximum, its value will be 1. Cos phi is equal to 1 means phi is equal to 0 plus minus 2 pi plus minus 4 pi, that is even multiple of pi. In general, we say phi is equal to even multiple of pi, 2n pi, where n for 0, 1, 2 like this. That is the phase difference phi. Again, the relation between phase difference and path difference, we know phase difference phi is equal to 2 pi by lambda into path difference del x. Here phi is equal to 2n pi. So 2n pi is equal to 2 pi by lambda into del x, or 2 pi cancel out, n lambda is equal to del x. So del x, that is plus minus 2n pi here, plus minus 2n pi in general, plus minus 2n pi. So del x is equal to plus minus n lambda. Here phi is equal to plus minus 2n pi. Here del x is equal to plus minus n lambda for maximum intensity, means for bright light. Therefore, what we say, here we write, we get the maximum intensity. The intensity of light is maximum. The intensity of light is maximum at those points where the phase difference phi is even multiple of pi, where the phase difference phi is the even multiple of pi. That may be a condition, or the path difference is equal to the integral multiple of wavelength, or path difference, the path difference is equal to integral multiple of wavelength lambda. Either phase difference is even multiple of pi, or the path difference is the integral multiple of lambda, then we get constructive interference. Where phase difference is even multiple of pi or path difference will be integral multiple of lambda, we get maxima or constructive interference, or for bright fringe. Now the condition for destructive interference, or for minima or dark fringe. For destructive interference, Same thing, here cos phi is minimum. For minimum intensity, that is for destructive interference, cos phi will be -1. For -1 condition, phi must be plus minus pi, plus minus 3 pi, plus minus 5 pi, like this. In general, phi is equal to 2n plus 1 pi, that is the odd multiple of pi. Phi is the odd multiple of pi. Again, we know that the phase difference 2 pi by lambda into path difference. Now phi, that is 2n plus 1 pi, is equal to 2 pi by lambda into path difference del x. Therefore, del x is equal to 2n plus 1 lambda by 2, when the path difference is the odd multiple of lambda by 2, and the condition for destructive interference. Look here, what happened in case of minimum condition. Here, in case of maximum condition, thus for maximum, thus I max, that is I1 plus I2 cos phi is equal to 1, I1 I2 2 under root I1 under root I2. Therefore, we have under root I1 plus under root I2 whole square, means I max is directly proportional here, that is for R1, that is for R2 whole square, sum of the amplitude square. We have the constructive interference. Similar thing happened here in case of destructive interference. Thus, for destructive interference, I minimum, the condition, that is I1 plus I2 minus 2 I1 I2 cos phi is equal to -1, which is equal to under root I1 minus under root I2 whole square, means I minimum directly proportional R1 minus R2 square. What we observe from this destructive condition, if the phase difference is odd multiple of pi, or we can say the path difference is odd multiple of lambda by 2, that will be the condition for minima or destructive interference. Let me write that important point. What will be the condition for minima? The intensity of light is minimum at those points where the phase difference is odd integral multiple of pi, or the path difference is odd integral multiple of lambda by 2. When the phase difference is odd integral of multiple pi, or the path difference is odd integral multiple of lambda by 2, that be the condition for minima or destructive interference. If we plot a graph in between the intensity and phase difference, if we draw a graph in between intensity and that for phase difference, the phases like pi, 2 pi, 3 pi, 4 pi and so on, minus pi, minus 2 pi, minus 3 pi, it is looking like this. Intensity always the same. Here the intensity will be minimum, other case intensity will be maximum. Graph between intensity and phase difference. Now, what will be the fringe width in case of Young's double slit experiment? Calculation of fringe width. Fringe width in Young's double slit experiment. Fringe width in Young's double slit experiment. Fringe width is the distance between either two consecutive right fringe or consecutive dark fringe. Let me look at the figure as we used here. The path difference be del x between the two coherent waves from the slits S1 and S2 reaching at point P on that of screen. So, del x here is given by del x is equal to, that is the distance between S2P minus S1P, is S2P minus S1P. What is S2P? S2P in triangle S2P, let a point here that is B, that is the point A. In triangle S2PB, that be the hypotenuse, that is base, that be the perpendicular. According to Pythagoras theorem, that square plus that square is equal to that square. Here, using that Pythagoras theorem, S2P is equal to d square plus this square, that is yn plus d by 2, from that to this, d square plus yn plus d by 2 whole square, it is under root half minus S1P. Similarly, S1P in triangle S1PA, that be the hypotenuse. So, its square is equal to sum of that square and that square, that square be d square, that square be yn minus d by 2, d square plus yn minus d by 2 square, it is under root. Taking d square as common, so d square it is under root, it is d to outside, inside that of bracket it will be 1 plus yn plus d by 2 whole square, it's under root, same thing here, minus d square as common and it's under root, so d to that of outside, inside that of bracket 1 plus, look here, 1 by d square, a term is 1 by d square, 1 plus 1 by d square, yn minus d by 2 whole square, it's under root. Now using binomial theorem to expand that term, using binomial theorem, as 1 plus x to the power n is equal to 1 plus nx plus dot dot dot, neglecting the higher orders, neglecting the higher orders. Expanding that term, we have d 1 plus 1 by 2d square yn plus d by 2 whole square minus d 1 plus 1 by 2d square yn minus d by 2 whole square. Or del x is equal to, or del x is equal to here that d is multiplied, so inside that of bracket term d plus 1d cancel out, inside that of bracket we have d plus 1 by 2d yn plus d by 2 whole square, again d is multiplied, d minus 1 by 2d yn minus d by 2 whole square plus d minus d cancel out, del x is equal to 1 by 2d as common, 1 by 2d as common, we have yn plus d by 2 whole square minus yn minus d by 2 whole square, a plus b whole square minus a minus b whole square, that is 4ab, or del x is equal to 1 by 2d 4 yn d by 2, 4 cancel out, the path difference del x is equal to yn 4d yn d divided by capital D, that will be the path difference del x. Now using the concept of the condition for bright fringe, the bright fringe for bright fringes, what we observe, let the point P on the screen will be the position of maxima, let the point P on the screen will be the position of maxima or bright fringes. What will be the condition? If the path difference path difference del x is equal to integral multiple of lambda, where n is equal to 0, 1, 2 like this. That is the condition for maxima. At point P, let we observe the maxima. What be the condition for maxima? That be the condition at point P to get maximum intensity of light. Path difference is equal to integral multiple of lambda, or path difference yn d by d, yn small d by d is equal to n lambda. Here yn is equal to n lambda d divided by small d. Here yn, that is the position of nth bright fringe. Here yn, that is the position of nth bright fringe. That be the condition for bright one. Now the fringe width, here we define in case of bright fringe the fringe width, that is the distance between two consecutive bright fringe. So the fringe width distance between two consecutive bright fringe. That fringe width beta is equal to yn minus yn minus 1, position of n minus 1th bright fringe, that is n lambda d by d minus n minus 1 lambda d by d. Under solving this, fringe width beta is equal to lambda d by small d. By taking bright fringe into consideration, we calculate the fringe width. Now taking dark fringes into consideration, what be the position of dark fringe? Dark fringes, the condition for dark fringes, let we take, let the point P on the screen will be the position of minima or dark fringes. If the path difference del x is equal to odd multiple of lambda by 2, where n is equal to 0, 1, 2, 3, not 0, that start from 1, like this, that starting from 1. Path difference del x is equal to yn d by d 2n plus 1 lambda by 2, or yn is equal to 2n plus 1 lambda d divided by 2d. Again, what be the concept for fringe width? Again, for fringe width, that is the distance between two consecutive dark fringe, that is beta is equal to, here yn minus yn minus 1th bright fringe. Here yn, that is the position of nth dark fringe. Yn, that is the position of nth dark fringe. Yn minus 1 is the position of n minus 1th dark fringe. Now putting the respective values here, we have beta is equal to lambda d by small d. That be the fringe width for two consecutive bright fringe. That be the fringe width when we taking two consecutive dark fringe. Here beta will be same. Thus the interference pattern consists of dark and bright fringes of equal width. Here we observe the interference pattern. The interference pattern consists of dark and bright fringes of equal width. Equal width with center of screen forming a maxima. The interference pattern consists of dark and bright fringes of equal width with the center of screen forming a maxima. And let me define a term, that is angular fringe width. Therefore a term angular fringe width theta, that is fringe width to that of distance between slit and screen d. Putting these values, we have lambda by d. Angular fringe width is equal to lambda by d. So the angular fringe width is independent of the distance between the slit and screen. There will be no such term of capital D. So what we observe from this Young's double slit experiment, look here, the fringe width is directly proportional to that of wavelength. As a simple example, if we observe the red fringes are much wider than blue fringes, since the wavelength of red light is much more as comparison to that of blue one. And again the fringe width is independent of small n. There will be no factor of n. Hence all the fringes possesses the same width in case of Young's double slit experiment, as we take that important point here. The fringe width is directly proportional to the distance of screen and the slit capital D, and inversely proportional to the separation between the two slits. An important point we have to notice here, if the whole Young's slit experiment apparatus is immersed in water, if the water have the refractive index mu, then the wavelength changes. Then what should be the fringe width? An important point here we have to notice, when Young's double slit experiment YDS apparatus immersed in water of refractive index mu. Young's double slit experiment apparatus immersed in refractive index mu, then wavelength lambda changes to lambda dash. Therefore fringe width beta is equal to fringe width beta dash is equal to lambda dash d by small d. Now putting its values, we have lambda capital D by refractive index into small d, which implies lambda dash is equal to, that be the value for beta, beta divided by mu, beta divided by mu. So the fringe width decreases in water and becomes 1 by mu times of its value from air. Fringe width decreases in water and it is 1 by mu times from air. So with the help of this video lecture, we understand Young's double slit experiment, experimental setup, and the explanation regarding how we observe maxima or minima. Then mathematical way, the condition for maxima and minima, the resultant amplitude, that is the intensity for constructive interference, phase difference is even multiple of pi, or path difference is equal to the multiple of wavelength. Then for destructive interference, phase difference is odd multiple of pi, or path difference odd multiple of lambda by 2, the graph between intensity and phase difference. Fringe width in Young's double slit experiment, we calculating fringe width. In position for bright fringe, that is the condition. Then fringe width by taking bright fringe into consideration. Then position of dark fringe, taking dark fringe, calculation for fringe width. And from this observation, the interference pattern that consists of dark and bright fringes of equal width, in which the center point is maxima, and angular fringe width. And if that Young's double slit experiment is immersed in water having refractive index mu and its wavelength changes from lambda to lambda dash, then what be the fringe width changes? That fringe width decreases as 1 by mu times of that of refractive index of air. So with this useful and informative notes, let me wind up this session. Thank you.